Good morning, students. Welcome to video lecture on electromagnetic waves and transmission lines. Subject code U18EC403. Topic: electric field intensity due to surface charge. Consider a finite sheet of charge on XY plane with surface charge density rho s. X, Y, Z. Here we have to consider a finite sheet of charge. Finite sheet of charge on XY plane. The radius of the sheet is A, and this is the position of origin. Uh, what we require is we are supposed to calculate the electric field intensity at a point P due to the sheet of charge. The sheet of charge is on XY plane. Along Z axis at a some distance, we need to calculate the electric field intensity. The coordinates of P is 0, pi, Z. To determine the electric field intensity due to sheet of charge, we have to consider a differential surface area, that is ds. Uh, Let it be at a point. If the surface area is very small, then this can be considered as a point. The coordinates of the point is rho pi 0 in xy plane. The distance from origin to the required point is a rho with angle pi. Pi is the azimuthal angle, and due to, first of all, what we have to do is we have to calculate the electric field intensity due to differential surface, and then we have to integrate to get the total electric field due to the complete sheet of charge. Uh, for that, draw a line from point P to the differential surface area P dash. The distance is r, and the position vector is ar bar. And along z direction, the distance is z. It is the distance along z axis, or in some textbooks, uh, this particular point can be represented by h, means at some height of h, you're supposed to calculate. Doesn't matter, both are same. Uh, the sheet is uniformly distributed with surface charge density rho s. Uh, the differential charge at the differential element ds. The differential charge dq at the differential element ds is rho s ds. Let it be equation number 1, and the sheet is on xy plane. So the differential normal surface, the magnitude of differential normal surface rho on xy plane, the associated coordinates are rho and pi. Uh, the differential surface is rho d rho d phi. Let it be equation 2. And before calculating the electric field due to complete sheet of charge, we considered a differential element ds. Due to differential element, we have to calculate the electric field at point P. Uh, we require the electric field at point P means the position vector associated with point P with respect to P dash can be written as minus rho a rho cap pi minus pi 0 z minus 0 z z a z cap. Let it be equation number 3. And r is the modulus of ar bar. It is equal to root of rho square plus z square here. Equation number 4. Once refer to the equation. Now the differential electric field due to the charge at the differential surface is given as modulus of dq by 4 pi epsilon r cube. It is the magnitude in the direction ar bar. Equation number 5. Then to determine the electric field E, it is the integral of differential field dq can be replaced by rho s rho d rho d phi divided by, if it is normal vector, you can consider r cube. R cube is rho square plus z square power 3 by 2, and ar bar is minus rho a rho cap plus z a z cap. Now here the integration limits are the integration is with respect to rho 1 pi. It is a double integral, a rho ranging from 0 to a, pi ranging from 0 to 2 pi. Now this can be once again simplified as here 1 by 4 pi epsilon naught is missing, 1 by 4 pi epsilon, uh, 1 by 4 pi epsilon, rho is from 0 to a. The integration of pi is from 0 to 2 pi, d pi is equal to 2 pi. So this term gets cancelled and we get 2 uh, rho s rho d rho divided by rho square plus z square power 3 by 2 minus rho a rho cap plus Z A Z. Uh, Once again, this becomes 1 by 2 epsilon rho is from 0 to A rho d rho by rho square plus z square power 3 by 2 minus rho a rho cap plus z a z. Here rho s is remaining. You can bring rho s out of the integral as it is constant. Now let it be equation number 6. Once remember equation number 6, from equation number 6 we'll start simplification in next PPT. Due to the sheet is uniformly distributed on xy plane, so due to symmetry on xy plane, the radial component is 0. The radial component becomes 0. That is the term associated with aero cap is equal to 0. Now it becomes E is equal to rho s z by 2 epsilon integration rho is from 0 to a rho d rho by rho square plus z square power 3 by 2 az cap. Here the direction of az cap is perpendicular to the sheet of charge. In general, you can replace with an cap also to represent the direction of resultant electric field, which is along the perpendicular direction with respect to the sheet of charge. It is equation number 7. Uh, from the calculus identity, integral of x dx by x square plus a square power 3 by 2 is equal to minus 1 by root of x square plus a square. Based on this identity, this can be simplified as E is equal to minus rho s z by 2 epsilon 1 by root of rho square plus z square, where rho is ranging from 0 to a. Let it be equation number 8. In the next PPT, we are going to substitute the upper and lower limits to simplify the equation. By substituting upper and lower limits and rearranging, we get the electric field due to finite sheet. The electric field due to finite sheet is equal to rho s by 2 epsilon 1 minus z by root of a square plus z square along the direction az cap. Now here, this is the equation due to finite sheet of charge. The sheet of charge is infinitely distributed on xy plane. That is the electric field intensity due to infinite sheet. For infinite sheet, the radius is infinity, then it is equivalent to rho s by 2 epsilon az cap. The sheet is on xy plane. We are going to calculate the electric field along z direction. Uh, this is the direction of the resultant electric field, which is normal to the sheet of charge. This can be generalized as, for infinite sheet, E is equal to rho s by 2 epsilon an cap. An cap is along the direction of along the direction which is perpendicular to the sheet of charge. Refer to the final equation. Once again, refer to the material available in textbook. He considered H in place of Z. Notation. Field due to infinite surface charge rho s by 2 epsilon 1 minus z by root of a square plus z square. Az cap units are volt per meter. In case of infinite sheet, rho s by 2 epsilon az cap volt per meter. Case 2, the area between the circles x square plus y square is equal to a square and x square plus y square is equal to b square, b greater than a. Means here it is a circle, it is another circle with radius b. The area between the circle is uniformly distributed with the sheet of charge rho s coulomb per meter square. What we have to do is we need to calculate the electric field intensity due to the sheet of charge, which is common between the two concentric circles. This can be calculated using this formula. Here to calculate the field due to charge distribution in concentric circles, you can apply, first calculate the field due to A circle and then field due to B circle. The resultant electric field can be calculated as EB minus EA. That is given by the formula. Thank you. We will meet with the next lecture.